No, no, that's fine.
All right, we can start.
Yeah, okay. Hello, welcome. Thank you very much for joining. And I will talk about FOSS and some experiments that we did with FOSS. So my first question is, who of you has heard about FOSS? Okay, who has written a FOSS program? Okay, I see. So I try to be with the terminology close to normal computer science terminology, because FOSS has its own kind of language. I try to be as understandable as possible. I will talk about the new synthesis. That's a project that's ongoing, and we try to understand the essentials of computation and find minimalistic ways to realize things and build a basis of computation. And for this, we built a family of FOSS-like languages with restrictions and certain properties. I will go then and talk about the ICE concept. I think most of you wouldn't have heard about this before, but it's about 20 years ago that Charles Moore, the inventor of FOSS, proposed the ICE concept. So we will look at this and see that other programming languages have this as well. And today I will focus on seedForth, which is in one of these languages in the family of things that we do. And the special thing about it, it doesn't accept text-based source code, but it accepts tokenized source code. And we will look into the details and why is this of advantage in the setup that we're looking at. Yeah, and then we'll do some summary, and we have probably time for question and answers. Yeah, I already said we want to understand the general foundation of computation. So how small can it be? Looking at von Neumann architecture and find out what is the essential really. And with a FOSS background especially, we want to know about the basic principles of FOSS. So what can be left out? There's an international standard, and of course you look at this following the quote from The Little Prince, take away what is not necessary and then you find perfection. And so we want to go there, make things smaller and have a sound basis and then let things grow again. So yeah, we want by this build a basis of a new modern FOSS, and I'm think about this morning's talks. So even a poem language or XP that we just saw could be implemented not just on LLVM, but on our basis. And so that's probably a nice thing. So within the new synthesis, we follow certain guidelines. So we want to express most of the things in FOSS. And if you think about it, it's a high-level language, and you can express function applications, and you can define data structures and so on. So we try to express as much as we can in FOSS, and we did this also with a cooperative multitasker that is normally supposed to be written in some low-level assembly language for the task transfers. So this is also done in FOSS. We strive to get some bootstrappable things. And one of the languages is bootstrappable and very nice. All should be completely transparent. So you could talk to us, and I say in 2 hours I can explain what's going on. If you have some FOSS background and computer science background, and then you can look at all the source code that we have, which is quite a small amount of source code, and you can understand what's going on. So it's completely transparent for you. Everything is accessible for you, and it's simple to understand. So we're looking for simplicity. And for this, we also look at analogy to biological things, for example, like how DNA is replicating, and we're thinking about this. And seedForth, the name, goes into the area of botanics, of course. So something is a small seed, and then it grows, and we will see how it grows. The technique that we use is disaggregation. So we see this complex systems. We try to dissect it and find the principles in isolation, and then we reassemble these in an appropriate way afterwards. So And on that way, we built a family of minimalistic stack-based languages. And I have a slide that compares the two that are in the title of this talk. That's preForth and seedForth. And preForth was the initial attempt. And pre says it's not really a forth because it has so many limitations. And you can see maybe as a key characteristics, the lines of code that you need to express this is 500 lines with preForth and roughly the same for the seedForth. So they are very small languages. And I'm not talking compiling to LLVM or some abstract machine. This is for the 386 machine code interface, which spits out assembly code, and then there is an assembler. The other key feature maybe is the number of primitives. So the preForth has 13 primitives, and this means many features are missing, like memory. It doesn't have addressable memory. It has to do all on the two stacks, which one is for parameter passing and the other one is for function called procedure return addresses. And because of this, if you want to do string handling, you have to do this all on the stacks, not in memory. So there are no memory representation of strings. You put them character by character on the stack and you deal with this, which you can assume is not very comfortable, but it works. And you have recursive functions in all of them. Also, preForth doesn't have any control structures. The only thing is that you have a procedure call with possibly tail recursion elimination and a conditional exit. And then you're up to formulate whatever programs you want. Both are Turing complete, so you can actually do this. And it turned out preForth is too simple, actually, to be the seed that we can grow everything out of it. Yeah, I tried this, and then within the discussion, we said, okay, no, it's not worth it. But it's suitable to build the next forth system, and that is seedForth. And seedForth now has memory. It has memory operators. It has some more primitives, mainly for memory and I think it's mainly memory and some other things, and it's only a little bit more in size. It has conditionals, so we have branching instructions as well, right? And so that's mainly it. And if you look at the data types, then preForth can only handle characters and integers, and you build up all the structures on the stack. And of course, if you have memory, you want to address the memory. You also have addresses. Right, so let's come to the ICE concept. That's something that in a talk of Charles Moore, if you listen to him very carefully in 1999, and I revised the YouTube videos that have been made at that time, and I came up with, right, ICE is what we actually are doing. That makes Forth and other languages very exciting. And the property is we have an interpreter that can take commands and work on them. We have a compiler that can take text and create code. And then we can even execute at arbitrary times things that we just defined. Yeah, and Forth has this property, but other languages like Lisp has this property. You do a function definition, next time you call it. In Forth, you define a word, next time you call it. And you can even, during compilation, you can go ahead and switch between execution and interpretation. So that's quite nice. Small example, I can define a function definition erase, which goes and initialize some memory with 0. Then I can interpret, define some constant buffer with an appropriate size, and then I can execute the definition that I just defined in there, and this will execute at compile time, when I process the file and compile it. So let's have a look at seedForth. The great thing about seedForth is that it accepts tokenized source code, and this means it doesn't need to have a parser or whatever to analyze text. So that's just great. It's about 550 lines of code, and you can extend it by doing function definitions. It could be recursive functions, so that's really easy. And because it follows the ICE principle, like all the languages that we do, it has a compiler that compiles definitions, an interpreter that can execute definitions even during compilation. So that's quite nice, and it's intended for building applications. And one of these applications is actually a full-featured interactive FOSS system with a read-eval print loop, a REPL, which is called text interpreter in the FOSDEM terminology. And we have i386 and AMD 64 implementation right now, but I experimented with the C backend as well as some symbolic backend, so you can stuff it into a list system and to get some execution. So here's the core slide that shows what it is. There's something that is created with preForth that is called the seedForth bed. Think of flower bed, yeah, so the botanic analogy. And that's the small core, 550 lines of code, 2K of memory. And this is 32-bit, so about 500 bytes is just the initialization of the table. So the code is really small. It's 31 assembly primitives and then some amount of additional things. And then you have 3 levels: the text-based source code at the top, tokenized source code in the middle, and then the seedForth bed on the growing seedForth system below. Also, we have, of course, operating system hardware support necessary to do some I/O or whatever if you have an IoT device to access the hardware. And so if you have source code of your application, it first will be tokenized. And then this token stream will be fed into the seedForth bed and it will be extended. But still it can do ICE. It can interpret things, it can compile things, and it can execute things on the fly during compilation. Yeah? The virtual machine that is about this looks like this. It has these 2 stacks, one for parameter parsing, one for return stacks. And instead of a parser, it just has a symbol table. The names of functions are tokenized into function numbers. And so to know, in order to know where a function actually starts, you just have an index access into the token table. The token table just captures the start addresses of the functions. And if you appear to see, okay, there's function 3b, yeah, actually coming, then you can go ahead and look up what its starting address, and you can compile a call to that appropriate thing. So we have data memory and code memory to do this, and several pointers that mark the 3 areas of this. So that's a quite simple architecture. And here are the seedForth bed words. I don't want to go into details of all of them, but the 2 interesting things for the ICE concept are the interpreter and the compiler. And what does the interpreter do? It accepts a token from the input stream, and then it executes whatever function is associated with that number. Looks up in the table, finds the start address, and then jumps to that, or does a subroutine call. And then it does interpreter again. So actually this is an endless loop, and because we have tail interpreter, it's tail recursive, so it will not spill up the return stack or whatever. The compiler will go accept a token, or maybe it's a 0, then we exit the compiler loop, go back to the interpreter loop. Maybe it's a lit, and then we'll do some stuff with the literal. But in the end, if it's not a lit, then it will just go ahead and compile a reference to the appropriate function, and then it's also loops. So the compiler is in a loop until it finds a 0, and the token interpreter will just go ahead and execute things. So we have source code, where we look at the source code, and we see here this is the hello world example for seedForth. So we just emit things, and we find in the tokenized thing also the string hello. We won't go into detail here very much. We can have a function definition, increment the top element on the stack. That is like this, and then we can invoke this already here. So again, we have interpret, compile, and execute of things. And if you look carefully on the previous slide, the next token in the sequence would be 3b. And ta-da, here's the 3b. That is the invocation of the, that is the tokenized of this, which will reside in the invocation in the compiler. So, and that's the output, of course. And so where is the ICE principle now being applied, really? That's when we have control structures. Control structures like begin until need to be compiled into conditional branches. Yeah, and yeah, in the end. So begin, the tokenizer takes function calls and makes single tokens out of it. And there are also macros that expand to sequences of tokens. And so begin expands to the sequence by here compiler, which means exit the compiler, do something in interpret mode, and then restart the compiler. And until expands to the sequence, question branch by, comma, compiler, which means compile branch, then leave the compiler and compile the appropriate address and then restart the compiler. And so if we look at the tokenization, then we see begin is 018824 and until will be compiled or tokenized to 15/00/2024. Yeah, and if we run this, then that's it. Right, so seedForth grows. You just feed the seedForth bed, plant new things in there, and we did lots of experiments with this. And so we have dynamic memory and many, many things like exceptions and cooperative multitasker and closure-like things and so on that you can build all on top of this. And that's a full-featured FOSDEM that I already talked about, called seedForth Interactive. You can all look up this up on the preForth GitHub page. Yeah, that's mainly it. So we want to extend this further, and if you're interested, come and get in contact with me so we can talk about this. So new targets, especially IoT targets, are on the way. New synthesis, the book. And yeah, thank you very much for listening, and I'm happy to answer your questions. Yes.
But there were also primitives in seedForth itself, written in assembly. Is that correct?
Yes. Yes.
Okay.
So preForth can actually take code words and colon definitions, and it will convert this to appropriate assembly language in the setup that we currently have, and then you use the platform assembler to create the executable in the end. Yeah, so it's these 31 primitives written in assembler, and then about 20 things among these compiler and interpreter to actually make this ICE capability available. Okay, thank you very much. Any more questions? Yeah.
So if you were to port this system to a new architecture, would you have to only rewrite preForth, or would you have to do set on top of each other?
Actually, you don't need to rewrite preForth because it's used to do the seedForth. It can run on the host system, but you need to rewrite the 31 primitives in seedForth. And the estimated time, because they are really, really simple, like moving here and there, is half a day for a new platform. So you can start reading the manual in the morning, and in the evening you have a seedForth bed system running, and all above is just machine independent. You can just load it on top. And it feels fast enough to work. You would think a small set of primitives would slow it down dramatically. No, that's not the case. The experience is it's really fine, good to use, and of high speed. Okay. Anyone? Yeah.
The source code is text-based, but how is it tokenized? I mean,
There's a FOSS program right now that does the tokenization, and one of the tasks that you might have seen on the slide is to rewrite the tokenizer in seedForth itself. It's already I already have a version in seedForth Interactive, the extended one, but we want to have it in seedForth itself, and then so everything is self-contained and the bootstrapping is there, everything transparent, everything available to you, no hidden things. Yeah. Yeah. Okay. Thank you very much. The mic.